Hello, everyone. Happy probably Monday morning to you, if that's when you're checking this out. It is now time for week 2 of Chemistry 20 distance learning. Hope week well went decently for you. I'll do my best to get those marked sooner rather than later and give you some feedback on them. In the meantime, let's continue. So guys, this week's been split into 5 sections. And the first 2, nice for you, are more of a review of stuff that you've done in Science 10. But they are really, really important topics. So I want to spend a bit of time focusing on them and making sure that you feel confident. And our beginning topic that we're going to do in today's podcast is a review of molar mass. Now, to clarify, if we're going to do molar mass, you better be feeling really confident on naming your ionic and molecular compounds. All right, let's start first about what molar mass really is. Now, reviewing a little bit about the mole, because that sometimes throws people off, is essentially a mole is just a really, really convenient number for thinking about the number of atoms or molecules or ions. And lots of things are like that. For example, think about socks. We think about socks and say a pair, and a pair is just a fancy number to mean 2. Or we end up with, there's a fancy name for this too, a whole grouping of copy paper out of 500. And it's 500 sheets for a specific reason because it's a helpful packing for the boxes. Or take eggs, they're in a dozen. And the word dozen just means 12. Well, mole is, again, just a fancy word, but it means 6.02 times 10 to the 23, which is kind of a crazy number. It's a massive, massive amount of, like I said, either atoms, molecules, or ions that make up 1 mole. Why so many? Because these things are small, guys. So it's helpful to have a whole lot of them. All right, let's keep going. Avogadro's constant works into this a little bit, and that's that number that I mentioned before. That's 6.02 times 10 to the 23 particles per mole. And when we say particles, we're saying that this could be atoms, like I mentioned, or this could be ions, or this could be molecules, right? All of 3 of those are categorized as particles. And ultimately, when you think about a mole, which we shorthand as MOL, then we're talking about just a convenient number of particles. Okay, do keep in mind, coming back from Science 10, the symbol we use for moles is N. And again, the unit, International System Unit for the mole, is MOL, which is kind of easy to remember. All right, let's keep going. Our focus today is all about capital M, which is molar mass. Now, molar mass of a substance is the mass of exactly a single mole of the substance. And check out the units for it. This is not new. You would have learned this last year. Grams per mole. And literally this means grams per 1 single mole. And the molar mass of a lot of different entities is really quite easy to find. If you have a single element, you just have to look on the periodic table. I gave you a couple examples there. So capital M reads molar mass of C, which is carbon, 12.01 grams per mole. Well, yeah, of course it is. If you look back at the periodic table, guys, and check out carbon, I'll zoom it in there for you. There it is. Carbon is 12.01. And if you ever forget what the units are, there's that nice little cheat sheet. Atomic molar mass, grams per mole. Okay. Move on, similar thing, molar mass of zinc, and this also would have come right off the periodic table, 65.39 grams per mole. Nothing new, but be aware of that capital M symbol. All right, I want you to also have in your head to recognize that a lot of elements are molecular elements. Those are our diatomic ones, or S8 for sulfur, or P4 for phosphorus. So a single atom of oxygen is, of course, going to be 16 grams per mole. Well, fine. But we know that oxygen is a molecular element, so it's oxygen gas, O2 gas, so we got to double that. Literally taking 16 times it by 2, there's our 32.00. We'll talk about that a little bit more in a bit, but I just want you to have it in the back of your head and don't lose sight of that. All right, let's keep going for actually doing some calculations. This cannot be emphasized enough. Write the chemical formula and do it properly. If you mess up the formula, molar mass is wrong. Guys, this is one of those stepping blocks of what we're going to be doing later. So if molar mass is down here, a whole bunch of other things are going to build off of that. If you can't get molar mass right, many of the other elements that we study in chemistry 20 and then into chemistry 30 are going to be extremely difficult to be accurate on. All right. Once you have your chemical formula, of course, pay attention to the number of atoms or the number of elements of each individual element. In terms of the atomic molar masses, we'll pull those off the periodic table, just like we were talking about. This is important too, guys. You must include the units. If you are leaving off units, your number doesn't mean anything. So please, please include it. Okay? Whenever we do the units for our molar mass, we'll have it to 2 decimal places. Okay, take for example our iron 3 oxide. Okay, it has 2 iron ions and 3 oxygen ions. So that's why we take the 55.85 and multiply it by 2. And then we add it to 3 times the molar mass of oxygen. That adding is really important, right? We have to put all the molar masses together. Notice when it's totaled. There's your units, grams per mole, and 2 decimal places. Be careful when you have a situation where there are brackets. Take aluminum nitrate, for example. See the brackets there? That means that this 3 that I'm going to highlight in green applies to everything in the brackets. So ultimately then, we actually have 3 of the nitrogen atoms, and we have 3 times 3, 9 of the oxygen atoms. That's really important to recognize. Okay, so this first one is relating to aluminum, the next one with times 3 is related to nitrogen, and the last one is related to the oxygen. Make sure that you're multiplying by the correct number of atoms or ions. Alrighty, let's try a couple of these and see what happens. So first things first, always make sure, like I said, you're naming properly. If a metal is involved, like it is here, then you're dealing with an ionic compound, which means you're going to have to pay attention to the charges and to balance them in order to get the correct formula. It's copper 2 plus, hydroxide is OH negative. You can still think of this as a drop and swap to do it accurately. I'm going to end up with 1 copper and 2 hydroxides. But remember, copper, bracket, because I have 2 hydroxides and it's 2 of the whole thing, and then put the 2 on the side. Okay, moving on, the way I usually write this is I'll write a capital M, and I'll normally actually put the formula after the capital M. This way I don't have to write it twice and it keeps me organized. Equals. All right, follow step by step with me. I don't always do all this work for molar mass, but for the beginning when we're reviewing, I will. We take the molar mass of copper, there's just 1 of them, so 1. Add it to, now notice with oxygens, they're in the brackets, there'll be 2 of them. So we're going to have 2 times the molar mass of oxygen. Plus, and again, we've got 2 hydrogens, so 2 times the molar mass of hydrogen. Now we need to actually start plugging in some values. Molar mass of copper is 63.55 grams per mole. Plus 2 times, that's where that coefficient's important, 16.00 grams per mole for oxygen. Plus 2 times 1.01 grams per mole for that hydrogen. In the end, we're going to end up with 97.57. This isn't good enough. You must have your units, grams per mole. Always, no exception, include the units, always 2 decimal places. Okay? Again, be careful. Remember that you have to multiply by how many there are of each individual atom or ion. Okay, check out another one. Let's go into nickel 2 carbonate. So like I was saying before, I normally would start this just by going M, and then I would write the actual formula, right subscript of the M. But think about your charges first. Ni3 plus and carbonate is CO3 2 negative. Right? If you don't think about those, it makes it pretty hard to figure out your actual formula. We're going to end up with, if you do drop and swap, that we're going to need 2 nickels and 3 of the carbonates. So we got Ni2 bracket CO3, and again, I'm going to have 3 of those. Think carefully about how many we have of each. 2 nickels is easy, 2 times the molar mass of nickel. Added to, carbon, be careful. There's not 1 carbon, there's actually 3, because you have to multiply by what's outside the brackets. Same thing, be super careful about the oxygen. There's not 3 of them, there's 3 times 3. So there's 9 oxygens. Start plugging in your numbers. 2 times 58.69 grams per mole. Remember, added to, plus 3 times 12.01 grams per mole, plus 9 times 16.00 grams per mole. When all those get added together, we have 297.41 grams per mole. Now, honestly, guys, I would expect as you get back into the habit of these again, that you could really do those step on your calculators, right? Literally, type in 2 times 58.69 plus 3 times 12.01 plus 9 times 16 equals, ta-da, you'll get an answer. But your accuracy for counting those different atoms and ions properly is absolutely essential. If there is any value in chemistry that is worth double checking and calculating again, it is 100% molar mass. Alrighty, let's do one more. Carbon tetrabromide. Take note, we got a prefix in front of the bromide, so this is a molecular compound. So we're not looking at charges, we're looking at prefixes. 1 carbon and 4 bromines put on there, okay? And we want the molar mass of it. Equals, well, same thing. Molar mass of carbon plus 4 times the molar mass of bromine, which means we have 12.01 grams per mole, added to 4 times the molar mass of bromine, which is 79.90 grams per mole, for a grand total of 331.61 grams per mole. And there you have it, folks, a grade 10 concept revisited. You should go into your assignments and you can now do all of number 1. However, I give you caution. I said I would bring this back to you to remind you of, please don't forget about those diatomic molecules. Specifically, I'm talking about Hofbrinkel, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Do not lose sight of those. In addition, these aren't diatomic, but still important. S8 for sulfur and P4 for phosphorus. You need to be on top of those. They need to be memorized. Check out number 1, like I said. Whoops, don't scribble it though. That's not quite what I meant to do. Instead, how will we highlight it? Number 1. There we go. Weekly assignment 2. Good luck to you. New topic tomorrow.